Hello students, in this lecture I'm going to discuss application of pumping lemma for regular languages. This theorem is basically used to prove that certain sets, or we can say that certain languages are not regular. Means it is used to prove that whether some language is regular or non-regular. The theorem it states that if we have a finite state automata M which has some states, n number of states, and there is a language L which is regular language, or we can say regular set. L is basically a set of strings, and here each string is of type regular. That's why we are calling regular set. Fine. So this language is accepted by the automata M. Now suppose there is we take a string W which belongs to L, and the length of W is greater than or equal to N. Here we are considering that W is a string. Fine. Then according to this theorem, we can divide this string W into three substrings X, Y, Z. Fine. In such a way that length of xy should be less than or equal to n, where n is the number of state of the finite state automata. Second condition should be that the length of y should be greater than or equal to 1. If we divide the string w in x, y, z, then these two conditions must be followed. After dividing the string, we apply x y to power I z, means we take some value of I which is greater than 0, then this string should belong to L. If a language is regular, then this condition will be satisfied. If x y to power I z does not belong to L, that means the language is not regular. Fine. Here we have taken two conditions. First one is that the length of x and y should be less than or equal to n. Why it should be? Now take this. See, we have seen a number of times that for accepting n symbols, we need n plus 1 number of states. For example, we take 3a's. So to accept 3a's, we need 4 number of states, Q0 to Q3, right? Now, if I increase the 1a also, means I want to read 4a's, then in this case, after reading first a, I'm going from Q0 to Q1. After reading second a, I'm going to Q1 to Q2. Now, for reading third a and fourth a, I'm reading these two a's at this particular state. Here I'm applying the concept of pigeonhole principle. Right? Pigeonhole principle, according to this principle, what happens if I have n pigeons and if I have n number of holes but I have n plus 1 number of pigeons, then I'll have to keep 2 pigeons in any of the hole. In same condition is here also. I have number of states 4, but for accepting 4 symbols I need 5 states, but here only I'm having 4 states, means at some state I'll have to read 2 symbols at particular state. In this case I'm reading 2 symbols here, means 2 a's at Q2 state. So I'm using here pigeonhole principle, right? Second condition is the length of y should be greater than or equal to 1. See, if we take y is equal to 0, then if we take y to power I, no matter what is the value of I, the value of y will always be 0. So it doesn't make any sense, right? So the length of y should be always greater than or equal to 1, right? Now let's take an example of this. Here, this is an example. Prove that this language a to power n and b to power n, where n is greater than 0, is not a regular language. Fine. So we will prove it by contradiction. Contradiction means we will first we assume that the language is regular, okay, and then we will prove that this particular means after applying pumping lemma, we will prove that this language is not regular. Fine. So let's take first step. First step is that assume L is regular. Okay. So, and where n is the number of states in finite automata that accepts L. So this is the first step. Second step is we choose a string W where the length of W is greater than or equal to n. Now we apply the pumping lemma here. The condition should be that we divide the W in x, y, z with these two conditions, that the length of x and y should be less than or equal to n and the length of y should be greater than 0, right? Length of y is greater than 0 or length of y is greater than or equal to 1 are the same thing, right? Now in third step we find suitable I. Okay, we find the value of I such that x, y to power I, z does not belong to L. Fine. Then L is not regular. Means if this condition satisfies that it does not belong to L, that means L is not regular. We have taken the example L is equal to a to power n and b to power n. Suppose we take the string W with 5 number of A's followed by 5 number of B's. See, this is the same language, a to power n and b to power n. Now we need to divide this string into subparts x, y, z. Here first case is that I am dividing this string. Suppose I take 3 A's as x, 2 A's as y and 5 B's as z. Fine. I have subdivided this string into 3 parts, x, y and z. Now if I take I is equal to 2, that is x, y to power I, here I is 2, x, y to power I, z, then applying this, the string will become now, here I am having y, I have 2 A's in y. Now I am taking power of 2 of y. Now I will be having 7 A's, right, and 5 B's, which is violating the language. Language is number of A's followed by equal number of B's. But after applying x, y to power I, z, if I am making this y to power 2, then this string does not belong to L. Okay, this is violating the pumping lemma. That means this language is not regular. In the second case, if I divide this string in such a way that x is representing 4 A's, right, and y is representing A, B, fine, and B is representing 4 B's. Again, if I take I is equal to 2, that is x, y square z, then in this case what will happen? See, I am taking here y to power 2, then it will be, I will be having 4 A's, then A, B, A, B, cause y is equal to A, B, fine, and then 4 B's. Then again what will happen? X, y to power z does not belong to L. Then we conclude that L is not regular. Fine. Now let's take one more example. The second example is, show that a to power I, where I is greater than or equal to 1 and I is a perfect square. I is a perfect square means the value of I is n squares. Means we can have number of A's we can have number of a's like a to power 2. We will be having, when n is equal to 1, then we will be having a single a. When n is equal to 2, then we will be having 4 a's. If n is equal to 3, then number of a's will be 9. When n is equal to 4, then the number of a's will be 16, and so on. Means the number of a's is the perfect square. Right? Now again we apply the pumping lemma. First step is, suppose L is regular and n is the number of states. Fine. Second step is, we take a string w, a to power n square. Fine. Where the length of w is greater than or equal to n square. By pumping lemma, we subdivide this string into x, y, z such that the same conditions we are applying here. Now, in the next step, we take I is equal to 2. That is x, y square, z. In this case, we have taken the length of a string is n square. Right? Now, here n can be any number. It can be n is equal to 3. Then in this case, the number of a's will be 9. If n is equal to 4, in this case, number of a's will be 16, and so on. So, the value of n can be anything. Now, length of w is equal to n square. That means n square is equal to xyz. Right? Now, n square is equal to xyz. We can write it like this. This. Mod x plus mod y plus mod z. Fine. Now, for I is equal to 2 means x, y square z, we can write it as, I am having here y to power 2. Means I can have 2 y's here. Clear? So, which is greater than n square? Obviously, n square was x plus y plus z. I am adding one more y. Then this will be greater than n square. Fine. So, x plus y plus z is n square plus n. Now, how is it n? Take this. The condition is that the length of y should be greater than 0. So, it should be greater than 0. Means I can take any value of y. Here I am taking that length of y is less than or equal to n. Okay, so here I am using the value y is equal to n. That's why I have written n here. Fine. See, manipulations will be taken according to the solution, means what we want to prove. Accordingly, you will have to take the values of y. Right? So, I have taken the value of y is equal to n here. Now, the condition is n square is less than n square plus y. Right? Now again, this n square is less than n square plus n, which is further less than n square plus n plus 1, n square plus n plus 1, which is again n plus 1 whole square. Right? Means this n square plus n belongs to, it lies between n square and n plus 1 x square. Right? And this is what? This is x, y square, z. Means we took this value. We took I is equal to 2. Then it became x, y square, z, which lies between two perfect squares. That means it is not a perfect square. If it is not a perfect square, that means that x, y square, z does not belong to L. Fine? It means L is not a regular. That's what we wanted to prove. Right? Now, you can try some more examples, like prove that a to power n, b to power m and a to power n, where n and m are greater than 0, is not a regular language. You can try it by yourself. Right? Now, there is a point to be noted. If a language is regular, then it always satisfies the pumping lemma. See, this is true for always. A regular language will always satisfy the pumping lemma. But opposite is not the true. Means if pumping lemma holds, it doesn't mean that the regular is that the language is a regular language. Fine. Hope this video will be helpful for you all. Thank you so much.